Blurry. Okay, thank you. And we are going to move to something that is going to be brilliant. So that's going to be our journey. And we'd start with something like this kind of thing, right? So from the blurriness to the shiny world. And our journey in what we want to show begins with quite an old image. This is a picture from roughly beginning of 20th century, more or less. And what we are going to see today is how we can actually turn this image into something that, again, is brilliant, is visually pleasant. And we are going to do this one through the usage of AI. And the whole story begins with something very old, I would say, where there was the human touch needed to make these pictures quite appealing or interesting. And this is going to be something that is a little bit personal, if you want to, because my dad was having a Photoshop. So I grew up living in his laboratory and see what he was doing with these pictures. And at the beginning, so 990, so sorry, end of 20th century, what was happening was that people were still using some very weird and fancy tools. So if you had a picture, a printed picture, that wasn't good enough because there were some issues with the papers, issues with the material that was being used to get the picture, the photo impressed in something. Then to correct it, you had to do a lot of manual work to put the human touch in it. And that begins with some very kind of fancy tools, but ultimately it narrowed down to the usage of a small brush. So you take the small brush, it's very, very, very tiny brush. You had another piece of paper or some other material where you take a little bit of a color and you bring the color to a picture. So it is a little difficult to see, but there are two white spots in here in this whole picture because of the printing process, because of the paper and the material again. So what the photographer was doing, he was taking the material from some other places and bringing it to the printed picture, okay? We were not working with something digital at the beginning. Everything was printed. And if you want to fix something as very simple as a red eye, that was quite common. When the first camera were out with the flash, it was quite common to flash a people and then you have these red eye spots. It often happens even right now at these times, but now it's quite easier to make them and fix it. At the beginning, it was really tough and it required lots of effort, a lot of time to make like a decent picture coming out of something that was already printed. And if you were a professional, well, things were even harder. Here we have two pictures of a very famous person. The one on the left is the original picture. The one on the right was the result that was put in a magazine. And to come from here to here, you see there are lots of notes, lots of things that people have to understand on how to change the color. And everything, again, was done on the printed picture. So imagine you have this little piece of paper where you see the colors and or not see the colors, and you have to fix because some areas are too dark, some others are too bright. So you have to intervene on any single position. So it was a really, really time-consuming process, really kind of spending days, weeks, if not months, on just changing something on a picture. So you need lots of experience, you need lots of skills for doing this one. And the work was really, really, really tough. But then luckily, there was a change in the things because we started to having like computers and machines that were able to ingest or to transform the analog things into something that was digital. And again, back in the past, when I was in the shop of my dad, what was happening, he was at the beginning scanning the picture. So the scanners were like cumbersome things. They were costly thousands and thousands of liras. I'm Italian. So it was quite expensive sort of a thing. So many of you probably are old enough to remember how costly was like a single megabyte of a hard drive where even the picture wasn't able to fit. So it was kind of interesting. So then moving the things to the digital world, then people started acting these things and practicing these things on the digital side. So this is a picture actually from my dad. I was able to find it somehow. So this is a very old picture that he was scanning. So he got this print and he was bringing it to the PC to fix it. So people was actually paying for these things, of course. You had this very kind of broken parts here. Here they're like parts of a scotch sort of thing or some tape sort of. And then the process was basically to kind of remove these things manually, but not by paper and brush, but by artificial paper and artificial or digital brush. And the result is kind of interesting. You still see some patterns here if you carefully look at that. But again, that was a really difficult task. That was at the beginning of the story. And this was certainly enough to get at least rid of these broken parts. And here's another example of the same thing. So you see there are lots of scratches, lots of things. But again, it was a manual thing. And even back in the days at the beginning, you didn't have the fancy pens to use on the PCs, but you have to use your mouse, which is a good interface for something, but it's very bad when you have to do these things. And again, if you carefully look at the things, there was this scratch over here. And if you, again, stare at the image long enough, you might be able to find some spots. Again, it wasn't perfect, but it was the beginning of the whole story. And then the story evolved quite fast, especially in the recent past. And people was not even more interested into fixing the old pictures, but it started getting very interested in how to make pictures more appealing for himself or for selling these pictures to be in a magazine, to be on somewhere. So there was a little bit of translation between the idea of digital touching or digital retouching, as it was thought in the past, where again, you have to fix an old picture that was scanned through a scanning system, brought into the digital world and somehow correct it. Now what it happens is that more and more people is getting interested into fixing what is already natively in the digital world. And this is done through a lot of, again, manual effort, manual process, at least a few years ago. You had a picture like this with a person with lots of things, let's say, on the skin. And what they would do, I mean, this is just an example that you can easily find on web, then the idea is to get the clean skin as much as possible, right? So it's more towards a sort of a personal appearance or personal interest of what is happening, that there has been a shift on this one. But then what happens, and we are skipping like lots of decades, probably, we move to the new generation of photo retouching or photo correction, where the generative AI is going to be overtaking everything. So now we see how these systems are going to be able to do the work that was done by person in the beginning, even the previous picture. So this is a manual work from some professional person that was staying there looking at the digital image and correcting and cleaning all the things on the skin of the person. Right now, what we want and what we are going to be looking at in the next few minutes is how this thing is shaping the way we see the images. And this is one thing that is going to be, that should be clear enough, is that these things are not only brought and used in the scientific domain. So lots of these things in our vision or imaging domain are also carried out by companies. So there are lots of companies that are funding, that are doing research on these things, and then they are bringing these results into their products. So there are things like this software, which I guess most of you know probably if you have done any kind of imaging on the PC or whatever. Then these systems are bringing in these generative AI solutions to do very weird things, but also very kind of useful things for people. As again, as we mentioned before, we had a person that wants to get the photo retouching of themselves. Now, like a simple swipe, let's say, of a model of an AI system, and what you get is a very clean picture with all the unpleasant, and let me quote quite heavily here, the details that are being removed, okay? So now the question would be, how is this possible? Because we are dealing with an image, and an image is no more than a grid of pixel, a grid of numbers. And how that possible then, by looking just at these small numbers that if you look at as a human naked eye, then you're going to be, of course, not able to understand unless they are presented in the form of an image. So the question would be how to turn these pixels into something that is a picture. So in the scientific literature, there are lots of different approaches that you can take to try to address these problems. And there are lots of kind of models or generative AI architectures that are based on what? They're based on neural networks. I guess that most of you are right now familiar, given also what happened in the past couple of days, right? You saw the 2 Nobel Prizes. And so what is happening is that there are these 3 kind of, let's say, big families of models that can be used to enhance, to bring some better visualization, better results to the imaging. So we had generative AI, generative adversarial networks, diffusion models, and what is known as variational autoencoders and normal flows. So in here on the right-hand side, you see like a time axis and what this was brought into the picture. But what is the nutshell of this one? Well, what these methods are doing, they are taking all this X as an input. X can be any signal, but in our context, X is an image. And what they are doing, they are basically reproducing kind of the same image, okay, but with some differences. And these differences can be totally new things. So I want to add something on that image. I want to remove something from that image. I want that image to be something else. And it can even be like the input is going to be noise in some of the cases. And I want to turn noise into something useful. And I'll do this one by combining the noise with some text. And this is what you are doing if you have been ever used DALL-E 3 or other generative AI models. When you input your prompt and you get the results, how does that work? Well, it takes noise, which is commonly available, plus some text, and magically it combines the 2 things to get out with a nice looking image. Well, there's, as usual, I would say, when we are dealing with deep learning and we are dealing with machine learning, there is a big problem. And that has something to do with the availability of the data, right? We cannot afford, in our case, to get lots and lots of pictures that are previously, let's say, corrupted, and pictures that are now in a good shape. Because that requires tons of effort from a human perspective, right? I cannot ask a person, I scratch a picture and then go and fix it by a manual person. It's going to be taking ages to just collect like a data set of, I don't know, 100 or 1,000 images, which of course, then it turned out not to be useful, because if I have just 100 or 1,000 pictures, it's going to be really tough to understand something meaningful. And then we'll see also why that's the case in the picture. So getting data is difficult and it's expensive. So there should be something that we should be able to leverage such that we don't need these things to learn how to fix an image, for instance. And one more important thing to say is that even though we have the label data, that's not always going to be the best solution ever. So if you have, for instance, a data set that is labeled and has lots of labels, lots of images, and if you use just that as a signal to learn something through your algorithm, that's probably not going to be enough, because your algorithm is going to be super duper biased on that data. And if you just do like a very simple trick as been done here on the slide, you teach a system to recognize something like an Indian elephant textures and a tabby cat, do like a mixtures of those. And you would at least expect that, okay, maybe the Indian elephant, the pattern is there, but I could definitely recognize the shape of a cat. And you don't even see the cat here. It says that there's a black swan, which is completely and totally different. So it has not even understood exactly what's in the image, right? It sees that there is a pattern, there's a texture, but it doesn't understand the content. Because if I wouldn't have shown you these things here, you would have said that probably this is a cat rather than an Indian elephant, right? So it doesn't make much sense. There is something hidden into those signals that is potentially bringing the understanding towards another side, which is exactly not the one we want. So the texture here is having like the prevalence, it's the most relevant signal that the model is looking at, which is probably good in some cases, in others might not be. So we need to find a way of figuring that out. And hence, the idea is that what the model should learn in the ideal world is that it shouldn't learn only from something that is very specialized, understanding cats and dogs. If I have a model that understands cats and dogs, okay, it's going to be nice, it's going to be great, but then it's going to be probably useless in most of the rest of the world. And probably I've spent like lots of money and things to come with that. Rather, what I want, again, in an ideal case, I want to have a model that could potentially be used for many different tasks. So it would learn by its own, like a baby, and then it gets some signals on what is good and what is bad, and what he has to do, what it doesn't have to do. But most of the things should be discovered by himself or herself. So the features that should be learned and should be encapsulated into an algorithm or into a neural network model should capture very rich characteristics that hopefully should be able to be exploited for other different tasks. So this brings into something very interesting. This is another famous slide from another famous guy that didn't win the Nobel Prize, by the way, though it was kind of one of the person that developed these things. And this is kind of a very famous, that's called the Lecan cake. And what it says is that there are different layers on these cakes. So one is what he called the self-supervised learning. That's the cake genoise, where there's lots of information. There are lots of things. There is much thing I can eat and use. Examples in our case, or bits. And then there is something on the top of the cake that covers it, right? That can be anything. And that can be learned by label, by data that is labeled. And that's going to be the cover. And I have a fewer bits per sample. And then there's the cherry on the top, which is, again, a few bits. What that means is that I can build a cake, but the most of the cake should be built by something that I don't have to pay for, that comes at no cost. That's a long story short. And so what people started looking at in the scientific community is, well, I have lots and lots of data. How is that possible that I cannot use that data unless it's labeled? So very smart move by very smart people. They said, okay, I do have that data. How can I cook up some labels artificially? Because a supervised signal is quite a strong signal for the model to learn something. So like if you have a dog or if you have a donkey, you use the carrot or you use the stick, right? And of course, it learns by doing that. It's not probably the best thing, but it learns that. So that's a supervised signal. What it is not good, what is bad. And so they came up with this idea of masking. So I have a sentence. So let's take the first example on top of it. I have a sentence. The man went to the blank. He bought a blank of milk. And that blank is actually known. If I grab a text, if I grab anything on the internet, I do have sentences like this, which most of the time makes sense, not all the time, of course, but most of the time makes sense. So if I mask these two things, mask these two words, and I use these two words as labels, then I do have a supervised signal that is coming from unlabeled data, because that's pure text. And it can be also a pixel, it can be anything. If I mask out something and I take that something as a label, then I should be able to design a model that, given all the rest of the things, generates a prediction or generates that missing label. And that's the way that people started cooking up some kind of fancy examples on how to use the data to generate what is also known as a label or a pseudo label to come up with a supervised task from unsupervised or unlabeled data. Another example is this one. So you have two sentences. The first one is the input. The second one should be the output. Or that's two input. Let me rephrase myself. So you have two sentences as input, and then you want to predict whether the second sentence is actually following the first. That's, again, something you already have in the data. It's not labeled. It's the data that is like this. Take a book, take anything, take Wikipedia, take whatever you want. That's already there. Again, most of the time makes sense. Hence, you can label that. Is this be the next sentence, or is this one the next sentence? And that's the model is, and then the model is taught on how to predict these things. So what does that mean then in our context? How is that going to be useful for the things we're interested into? So how can we use this information from making that quite old picture of the two men in the seat looking nicely? I don't have the data for that, I told you. We would have need to ask to thousands of photographers all around the world to generate that data for making something label. Again, wasn't possible, it's not possible. So there's something on the things I just shown that probably is going to be useful for that. And the tricky part is that you really have to think about carefully how to generate that useful data. So let's start by placing the colors on the image. So this is a common image that you will ever find. Take any image. This is just not a pure example. Okay, this is an image in the RGB space. That's a common way we see images on the computers. But an RGB image can also be projected onto another color space, where one plane of that image is going to be the grayish or the lightness channel, and the other two things are going to be the portion of the image or the original image that contain the colors. Okay, so I have an image that I see as a colored image. I take out the colors and separate them from the lightness. All right, so I have these three channels here. And magically then what I can do is I can possibly use this as things as the input and output, right? If I have this one as my input, then I can predict the two colors. I then recollapse them all together and I generate a colored image. So I can leverage this data that is completely unlabeled. You can take any image over the internet again, or any picture you have on your smartphone or cameras, project into this different color space and have these three guys over there and then use them to learn something. What is the problem? Well, there's a big problem here. When you transform something from the color to the gray scale, when you remove the colors, these two colors by definition of the projection to the grayscale color space, are going to be having the same value. So that's going to be very tricky. I cannot do the same things opposite-wise, because then I would have one color that projects to two different alternatives. And this is just one example. You could have many, many, many different examples. So there is no gray to RGB inverse function that I can use to magically provide the colors to an image. So there's going to be a big problem. How the hell I'll be able to find a way to get back, because I have multiple projections from the same pixel value? Well, the things you have to do is you probably have to learn something from the context. I cannot just take a pixel value, but I should look at some neighbors. I should look at the entire image. I should look at something else. So this is something we did kind of a few years ago. So we have an image here, and we cook up very, very crazy architecture that does lots of different things. It's based on convolutions, and it uses other concept known as capsules that would leverage and capture the entities of images or of objects that are in images, and leverage all those things to do what? To, again, produce those two famous channels. So it takes the gray as an input, and it produces the two colored channels in output. You combine them together, and again, you get a tiger, a colored tiger. And what does that mean? Well, what it means is that you can do things like this. All the results that you're seeing right now were grayish input. There were no colors. And magically, just by learning on unsupervised data, unlabeled data, probably unsupervised, not right, because you have self-supervision, but unlabeled data, you would have been able to generate and put colors into the things. Though here the sky, probably the variations are different, and here as well, or quite similar to each other, given what we saw with the previous gray and red blocks. But by leveraging on the context, understanding what is there, then it assumed that this is like sort of an orangish, grayish cat, rather than being a black one, because it probably understood that the stripes are characteristics of that things, or that the dog is brownish and this is white because of the snow, for instance. So the model has learned something useful that has been used then to generate the things. But in our story, we're mostly interested into old pictures. So another thing we tried is we took very old pictures by famous photographers. These are historical archives. And we tried to give the colors. And then it was really interesting to understand and see what the model was doing. Because one thing is work on the grayscale images that are taken from kind of smartphone or cameras. And one thing is taking grayscale images that are taken by other means, old-fashioned cameras, digitalized photographies, and so on and so forth. So you still see some of the results. These are this is an extinct animal, by the way. So there are kind of interesting things in colors that could be assigned to even animals we have never seen, we are not seeing any longer. So it's going to be quite interesting. And in our case, what this turned out to be. So let's proceed in our story. Well, if you start giving the colors slowly and slowly, you get to see something like this. Okay, it removes the yellowish things, and it assigns the more kind of ideal colors, which were like black or dark shades. Skin is quite white, I would say, but there's still something we can do. And one more thing that you might notice probably is that there's another problem with these pictures. They are quite low in the spatial resolution. Okay, they are old pictures. They're probably digitalized through scanning systems that were cheaper and not professional. So the quality of the image in terms of its spatial resolution is quite low. So there are not much details. The image is quite blurrish. What can we do with that? Well, what are the details then? I want to see the details. I want to see that picture quite nicely. I don't want to have a blurrish thing, such that if I could take a printout, though probably people's not longer taking printout of pictures these days, but if I would like to do that, then I need a high resolution thing. Okay, so then I start with some example, probably it's familiar to many of you in the field, hopefully. What I want to get is that I have a low resolution scan or picture take from some satellite or some other system, and I want to bring it to kind of a good resolution where I can remove all the noise, when I can see all the possible details. And how can I go from here to here? Well, there's a family of methods that's called super resolution. And here is one example. What these methods are doing, they are scaling up the resolution of the images. Again, I cannot afford to take two pictures of the same scene with one low resolution and one high resolution camera. They should be perfectly aligned. That's super costly. I don't want to put two devices in the out space, for instance, for doing these things. So what I need to understand, again, how can I use the data I have to come up with something that would be useful for that thing, to get me to the details? Well, this is a quite simple scheme, but what people is doing is that you have a high resolution image. You create artificial degradation and downsampling such that you have a low resolution image. Then you feed these low resolution image to something. It can be a black box in our case. Let's think about this way. And maybe you feed the artificial degradations. And this guy here will generate you the high resolution image. And then what I would do is I would try to see if they match. If they match, it has done a good job. If they don't match, again, that's a signal that the black box can use to kind of do better. And in the literature, there are different ways of dealing with this one. Non-blind, explicit, and implicit. All of these have different kind of capabilities and could be useful or not in different approaches. The most interesting, which I'm going to show like a slide in the next minute, is when you have a network that estimates something that has done the blurriness, and you use that for super resolving. What does that mean? That means that I can take any image, apply any possible degradation I have in mind, and my model should figure out what was that degradation and how to use that one to go back to the high resolution case. So I don't have to provide any ground truth, any labeled information. I don't have to provide any information about what was the degradation progress. Because in reality, you could have images that have been degraded by different ways. One can be noise, can be compression by an algorithm, another can be blurriness, another can be motion, whatsoever. So the degradations are quite a large number. So by coming up with something that, in this case, estimates are like a blur kernel implicitly, so within the model, it estimates what was the blurriness kernel that was applied to the image to get this low resolution thing. And then what we would do is we'd exploit that information with, again, fancy operations here and there to ultimately generate the higher resolution image. So then what I can do with all these things? With all these things, then I can go back to my example, and this is going to be the closing thing. I would first probably, again, step by a second to the colors to see what we have done. And then I want to see the details, and I want to see the better colors. And again, magically, if everything works, I should see better details. I hope you could have got it. It's quite subtle, but if you look at that, there's going to be more details. I can show it on the laptop. This is not good on the projector anyway. This is another example, picture of an old guy. And if you do the magic transformation, you start to see the colors, and the air is probably better to see the details. So by using only the data that is available without any information on what is in here, how is that cooked up, how is that picture taken, and so on and so forth. So you're able to transform these things, okay? So from a very old pictures, you can come up with a colorized high resolution image. And so this concludes my talk. I hope you enjoyed it. And this is, of course, not the work of only me, but it's a work of our group at the neighboring University of Virginia. So I would like to thank you, my collaborators as well. So thank you for your patience.
Okay, thank you for your nice talk.
Any question, please?
For questions? Thanks for the nice talk. I wanted to ask you, you showed that this super resolution pictures for this density maps for the universe, this PNAS paper. So, uh, so this is not a question, but also like a kind of like asking you for a suggestion. So because, so let's say the RGB images, so usually they have, let's say, pixel values between 0 to 255. Yep. It's almost like standardized. But this kind of images, they usually represent the photon counts. It could have 0, it could have 10,000, whatever, blah, blah, blah. So do you have any suggestion for scaling these images? Like, because so let's say when I process the images for the super resolution, diffusion, denoise, whatever, blah, blah, 0 to 255, I scale, divide by the maximal value. Everything is between 0 to 1. The pixel values look Gaussian, but here it will not be like this. Any suggestions for scaling this kind of images? We have a bit of trouble with this.
Okay, that's an interesting question. Okay, so first of all, let me clarify that I'm not super familiar with the topic, so it's quite interesting you're bringing in this problem. I didn't know that, so again, super duper interesting. For that point, what I would probably do is I would try to understand if the model could learn that as well. So is that really necessary for me to scaling the things down? Or could I leave the model to predict any possible real value? Because the model can predict anything. You don't have to restrict the model to predict values between a specific range. Scaling down, it's useful because you're constraining the projection somehow. But if you don't have that constraint, I would try to figure out if the model can do learn by itself. Because it can potentially predict values that it has never seen before, so you're not constraining it. Okay, good. You're welcome. Yes, please.
Hi, thanks for the great talk here. My question was also with regards to this slide and the next slide here. From what I understand, if you could just move to the next slide, actually, because yeah, essentially.
This one or the next one?
Maybe the next one. But okay, they're all identical, essentially. Yeah. So here I understand that the network's trying to understand. It's essentially learning to undo the degradation that you've done, right? So it's specific to the kinds of degradation that you've trained it on, right? So you had mentioned, I guess, 2 slides after this, that it's quite robust to any kind of degradation that you would provide it. But it's only, I mean, that you might encounter in real life, but only if you've already taken that into account. So you need to know the kinds of degradation. You should be able to model the degradation very well, right? So when we're going back to the science case that you were showing us, we need to know the ground truth, super high resolution, to be able, or at least we need to know how do you basically go from the high resolution to the super high resolution? Because there, what kind of degradation? It's not really a noise degradation. It's just you perhaps just don't have a very accurate simulation. So I'm failing to understand how you could make more data, add more information when you don't have that information.
Yeah, that's a good question. That's a key point. So everything that you have to learn or unlearn through this model comes from how good you are in making this one. Because I can skip this one and I just do bicubic sampling, and there's one case of kind of degradation as well. But in the context of natural images, what you would do is you would try to mimic as much as possible the degradation we would encounter in real life. So it could be noise, it could be blurriness, it could be like JPEG compression. So you are kind of injecting altering transformation. And this is something that you have an assumption. That's a strong assumption, I agree with you. But that's the only way that right now we are able to cook up some data. That's probably not the best, but somehow it's working, even for kind of degradations that you have maybe never known. So you don't know exactly what's the degradation for an image because it's taken from a camera, it's a low resolution, right? When you take that, it could have been gone through a different process, so you don't know what is that. It could be the lenses of the camera, it could be something else. So you have never seen that ideally in your test case. Though, if you mimic enough of these degradations, maybe as a mixture of those or something, the model would unlearn or learn how to undo that.
questions here? I don't see it. Sorry.
Thank you. No, I think this is really a great also discussion for this audience here, right? Because like this artificial degradation that you show, it's crucial. So if you have some domain knowledge, if you know what the physical processes are behind this, that's great, right? And here is where, like, I don't know, physicists can bring their knowledge in order to make this images like this process adaptable to their problem, not the general one.
Absolutely.
Right? So this is something that is really great for this project. But I would just ask you about like that arrow from artificial degradation into that black box. Because in the inference stage, you only have the image. You don't have that arrow, right? So how do you deal with that? What is the role of this artificial, of the role of the knowledge? How do you degrade an image into this upsampling scheme? Because in the inference stage, you don't have that.
Yeah, it's true. You don't have. So some methods are using that when they are dealing with the things explicitly. So they assume they do know the degradation process. So they know the kernel and they know that thing. Then they are putting it even at the test stage. That's a little bit sort of a cheating problem because in the real world, you don't have that. But at the beginning, at least, now the models are shifting towards mostly what I showed you. At the beginning, it was fair enough, at least to understand exactly what we can do with these things. And then you can start removing something, ideally, to get as much as good as possible.
I wouldn't call that cheating. I would call that introducing domain knowledge into the image.
Yeah, but it's going to be really tough. I mean, you cannot assume that everyone knows exactly what was happening. Yeah.
But at least model of the gradations. It's, yeah. Oh, okay, thank you.
Yeah, and good point, by the way, on the fact that this is domain knowledge is going to be quite useful. And yeah, and I hope this one was helpful to any of you because you're coming from different fields. So understanding where you can put your efforts could be quite useful. So thank you, Daniel.
Yeah, exactly. So I wanted also actually to comment on this. So exactly. So in physics or whatever, astrophysics, it's good. I mean, we do have in theory good high resolution models. And we have lousy images from telescopes that we would like, I mean, might want to bring back closer to the models. But then also in science, uncertainty, sort of estimating maybe per pixel or like how uncertain it is in the network and then bringing back to high resolution is also critical to interpret data properly. And I guess this is not, I mean, worry yet. I mean, for in your field or not worry at all.
Yeah, in this field is not as critical. It would
right, of course.
So it has been applied also in medicine or some other fields, but it's a little bit more critical. So instead of just looking at how good the model is at predicting the pixel values, you want to understand how kind of certain or uncertain or how trustable is that model. So there should be other techniques which could be applied on the top of this one or together with this one to introduce something else, because that depends heavily on the problem you have.
Okay, and then just a very, this is just a popular question now.
Please.
I felt like mentioning deep fakes. And I mean, given that you work in the field, relatively speaking, just popular comment on like what is the chances in spotting, like now that you're entering the age of deep fakes, you know, this also makes it completely clear that it's so easy to do, like entangling.
It's going to be tougher and tougher and tougher to understand.
I mean, is it even possible? Like, do you see any like smoking gun signature or whatever, like, you know, any way, any path to actually saying what was, you know, the level of manipulation of a visual that we get?
Understanding the level of manipulation, it's doable in some cases. It's not totally not doable in the others. And then you have to assume that everything you see, you have to check it. And that's not possible. So, unless you have a filter on your TV or on your desktop that for every frame it sees, it tells you that is that good or not. By naked human eye, some things are really difficult to differentiate, let's say.
Okay, thank you. We will move on to the next speaker.
Thank you.